Hello, welcome to part 2 of deriving the Lagrange equations. So it's been a while now since I uploaded part 1, but if you remember we started using Newton's second law of motion, F equals ma, and we also used the formula for work done, and we've thrown in a bit more complicated notation, and we came to our final equation number 2, okay, which seems quite long, but hopefully it makes sense, all the steps I did in the first video, and if not, you can go back, rewatch it again. If you don't get it that time, you can rewatch it again, and hopefully it will make sense to you. There is a lot of notation, but you know, overall it is quite simple calculus really. So yeah, what we're going to do now is we're going to look at the cancellation of dots, and once we've proved the cancellation of dots, we can then use it to finish deriving the Lagrange equations. Okay, so let's get started. To derive Lagrange's equations, we want to show that the term in the square brackets, okay, in the last equation we derived, can be expressed in terms of derivatives of kinetic energy. Okay, that's our main goal. So the kinetic energy, as you know, is a half mv squared, or it can be written as this, a half mk r dot times r dot. Okay, so if we differentiate equations with respect to velocity q dot j, our generalized coordinates, okay, we're going to get the partial derivative of the kinetic energy with respect to q dot j. Okay, this should be quite basic. We're going to get mk r dot multiplied by the partial derivative of r dot with respect to q dot j. Okay. Right. So perhaps the least intuitive step in the derivation of Lagrange's equations is noting that the last term in equation 4 satisfies the following identity, known as the cancellation of dots. So we go back to equation 4, okay, there it is. Okay, so this last term right here, this partial derivative, will satisfy the cancellation of dots, okay, which is, I find, a really neat tool in calculus. It's really clever. It basically says that the partial derivative of r dot with respect to q dot will equal the partial derivative of r with respect to q. You basically just get rid of the dots and they're still equal. Okay, so what we're going to do is digress briefly to derive this equation. Okay, so it'll be very brief. You don't actually have to watch me derive the cancellation of dots. You can go forward and just carry on with the derivation of Lagrange's equations, but it's very useful to get a bit more insight into the cancellation of dots. Okay, so let's do this. Differentiation of the transformation equations gives r dot k is equal to the sum of the partial derivative of r with respect to qj, q dot j, plus the partial derivative of r with respect to t. So the transformation equations were very simple. Here they are. Okay, our position r is equal to r with our q1t to qnt, and we have a component of time there. And yeah, that's it. Okay. And of course we have the transformation equations of our velocity here. Okay. So differentiation of our first transformation equations of the displacement, we're going to get velocity. Differentiate displacement, we get velocity. So r dot k is going to equal the partial derivative of r with respect to qj multiplied by q dot j. Okay, differentiating our q. And then remember we had a component of time, so we just differentiate r with respect to time. Okay, so which shows that the function r dot k can be expressed as a function of the following form. Okay, this is our second transformation equations, if you like. Okay, so we differentiated the one I showed you, and so this obviously shows we can write r dot k in this form. Okay, we have q of t to q nt, we have our velocity, and we have our time. Okay, just using the format of this equation. Okay, hopefully that makes sense. So differentiation of this equation 7 with respect to time will give us this. So dr dot by dt is going to equal the partial derivative of r dot with respect to qj times the rate of change of qj, which is q dot j, plus dr dot by dq dot j times the rate of change of q dot j, which is q double dot, and then we add partial derivative of r dot with respect to time. Okay, very good. So that's the multivariable chain rule into play there. Alright, so hopefully you got that. You can rewind if you didn't quite understand that, but we're going to carry on now. Okay, so whereas differentiation of the equations 6 with respect to time, okay, differentiation of equation 6, so here's equation 6, okay, this is just a different way of writing r dot k. We had r dot k in the form of the transformation equations. Here we have r dot k in of partial derivatives, okay. So doing exactly the same thing we did with the transformation equations, if we differentiate this, okay, equation 6, where are we? We did this, hold a minute, oh yeah, here we are. Differentiation of equation 6 with respect to time will give us this. Okay, brilliant. So the first and third terms in equations 8 and 9, so 8 being what we just did, differentiation of this, okay, with respect to time, and we also did the exact same thing but differentiated the other equation with respect to time. They're both equal, they're both dr dot by dt, and we can see that the first and third terms in both those equations are identical. Okay, dr dot by dqj and dr dot by dt are also shown in here, dr dot by dqj and dr dot by dt. Alright? Okay. So the remaining terms can be the same for all motions, only if equation 5 holds. Okay, equation 5, I think that was our, yeah, that was it, the cancellation of dots. Okay? So the remaining terms can be the same for all motions, only if equation 5 holds. Okay? Thus, the cancellation of dots identity in equation 4, we find dt by dq dot j is equal to this. Okay? Just using the cancellation of dots, we just cancel the dots from the dr dot and dq dot. We can get rid of them, and we just have dr dot by dq. Alright? So that's the derivation. I could have just told you the cancellation of dots, but it's always good to do a derivation. So basically, if you remember, I'll go back. You probably did remember, but remember, we had the partial derivative of t with respect to q dot. We had this, and then just by implementing the cancellation of dots, all we do is get rid of these two dots above the q and the r. Very simple. Okay? Right, so let's get, glad I've got that out of the way. Okay, almost done. Alright, so this is where we are at the moment with our kinetic energy. So, another differentiation of equations 10 with respect to time, okay, gives us this, d by dt of the partial derivative of t with respect to q dot j. So just taking the time derivative of this, okay, you should be able to do this. It's m times r double dot, differentiation of velocity, multiplied by dr by dqj, okay, and we add this term. So we're using the product rule, okay, differentiate that, multiply by that, and then we differentiate that, multiply by that. Okay, using the product rule for derivatives. Okay, so see, this format looks quite similar to Lagrange's equations, so we are coming somewhere. Okay, so where the last terms is simply dt by dqj. Okay, so the last term, dt by dqj, okay? Sorry, yeah, where the last term is simply dt by dqj, hence the rate of change of the partial derivative minus dt by dqj will equal this. Okay, if that makes sense. So dt by dqj, okay, is this term here, dt by dqj. That makes sense. Okay, so I'm trying to think of a way to explain this. So we had the partial derivative of t with respect to q dot j gave us this. We take the time derivative, okay, we're going to use the product rule. And that gave us this. This n term is the partial derivative of t with respect to qj. Therefore, we can take it and put it onto the end here. So we're left with the first term we had, okay, here. We basically take this term, and put it onto the other side of the equation, and we're left with this one. Okay, so we're simplifying things here. Okay, you can check that yourself, that dt by dqj is the last term in the other equation. I think it's equation 11. So, substitution of equations 12 into 2. So we have to go all the way back to equations 2. Here they are. Equations 2. So what are we doing? We're substitution of equations 12 into 2. Okay, so we have, you can see we have the first term in the equation in front of the equal sign, and we minus q times dq by j. Equations 2. Okay, so basically this here, this right here is, of course, this here. So we can substitute that into equations 2 and we get that. And of course you take the q and put it there. This term is equivalent to this term. Okay, and we can of course rewrite it in terms of partial derivatives, which we have here. And we just basically take the q term and set it equal to 0. Very good. So, because the variation of our